So I like relays. They're big, they're chunky, there's something old-fashioned about them, they click when they're working and you often get a light on to tell you that they're actually working. So I think they're pretty cool things. However, it surprises me how similar these are to transistors. In fact, in their logic, I would argue they're identical. So if you want to get hold of transistors, which can very often a mysterious black box, then you could do worse than work with relays a little bit because the logical principles are identical. So much so, if you wanted to, you could build a computer out of relays. I mean, it would be the size of a small city because it's electromechanical prone to failure and take a hell of a lot of power. But you could do, that's the point. So understanding relays is a direct link to understanding and building circuits in transistors and integrated circuits, which is why I think it's kind of important to have a look at a relay and use relays to construct the kind of circuits you'd find in an integrated circuit. And of course, we are working on clocks and we need a timer circuit and a counter circuit and a frequency divider. We can do that with relays, or we could just buy a clock chip for about £4 from Amazon. But you wouldn't really understand what was going on there. And I think using relays to build those circuits helps understand what's happening in transistors, integrated circuits, and a whole lot of black box mysterious circuitry. So relays are surprisingly important. Now, of course, we can't carry any analogy too far. When does a table become a chair? There are points at which it will fall down. One of them is that the relay is a make or break contact that is fairly instant, and so it's kind of a snap and quite sort of brutal at that. A transistor doesn't quite work that way. When you feed a current down the base, it begins to turn on around about 0.6 volts. About 0.7 it's ideal, about 80% saturated, and about 0.8 is where you're getting to the maximum of what you really should be putting in the base of a transistor. And that will be reflected in the current it allows to flow between the emitter and the collector. As that current varies on the base, the current flowing in the emitter and collector will vary to the same degree. And so a transistor would be brilliant for audio amplification. This would be rubbish. You can power amplify because amplification is actually a bit of a misnomer. It's not increasing the power. What it's doing is using a higher power line that it's controlling, but still it amplifies. So they both switch. This would amplify, not well for audio, but it will amplify. And they're working in the same way. You put a current into the base to turn on a switch. Here you put a current into a coil to turn on a switch. It allows current flow between emitter and collector, and this allows current flow between common and normally open. So logically, they're the same. Functionally, they're pretty much the same. Mechanically, they're different, and that'll lead to quirks in the construction. Now, as I say, these are power hungry and electromechanical, so there's also quirks in how long they're going to last, which is why really transistors have taken over. But when we look at designing circuits, we'll look at a relay, it'll give us a very good clue to how to design for transistors and what transistors are doing in their mysterious black boxes. First of all, let's have a look at a latch. Now, you wire a relay as a latch like this. Once you've wired it all together, what you get is sitting right here on the table. And what happens with the latch is it's currently being fed with power and it's doing nothing. It's not lighting that switch. But if I press this switch momentarily, the light lights up and it stays lit even though I'm no longer pressing that switch. If I then press this switch, which breaks the power, of course it turns off and stays off. The latch is one of the fundamental circuits of digital electronics. The latch and the flip-flop. We'll deal with the flip-flop later. But the latch is able to display information. The information here is the light is on. But we can also store that information other ways. Now, if I'm pressing a switch, it's identical if I press a switch or send a signal down a line or a pulse down the line to send a brief pulse into the coil, which operates the switch, keeping the power constant. This breaks the power and of course it goes off and stays off. So it's in two stable states. Pulse, stay on, pulse, turn off. We have a 1 and a 0 controlled by pulses sent down control lines. Now, if you tried to do something similar with a transistor, I imagine it would look something like this. Unfortunately, that won't work. And that won't work because the voltage across the base emitter and collector is all the same, and we need a different voltage on the base in order to get forward bias. The most common approach is actually to use two transistors like this to create that latching circuit, though I imagine if you put a limiting resistor on the base of the one transistor, you would still get a latch circuit. In order to create a flip-flop, you take two double-pole double-throw relays and wire them together like this. Once you've wired them together, you get what's on the table. And this one uses a single input pulse rather than two input pulses, and that's represented by this micro switch here. If you watch the top of the relays, when I press the switch, you'll see the green LED come on. That green LED comes on there, stays on obviously, then that one goes off, and that one goes off. And what it's actually doing is counting. It's a binary counter. So if I put 5 of these together in a row, I'll be able to count from 0 to 63. So if we generated a frequency of something below 1 second, what this will do in 5 of them in a row, obviously, what this will do is count a minute. It'll then send an impulse on the out, where we've labelled next stage as the out impulse, to something like our motor once a minute. Then it'll reset itself and begin the count again. And if you wanted to implement that in transistors, it would look something like this. Now, as has been pointed out to me many times, I probably spent about £20 on relays, and I could have done the whole job much better if I'd just bought a board for a couple of pounds. But that's not the point. You're quite right. It would do the job a lot better, but I think there's a guttural feeling in relays to how they actually work. You get to see and feel and hear the clicking of the switch, and all digital electronics is really just switches. How you arrange them, how you turn them off and on, and how you interpret their switch position is where we get the rest of the information, but that's got nothing to do with the actual electronics. The electronics is switches turning it off and on, and I think you get that sense by using relays. So in this one, we can pull off of relay B, pin 4, a state, that is whether it's off or on. A 0 or a 1 is how we would interpret that, and then of course that becomes a binary representation of the number that's actually in that relay, because that relay remembers its state. That is, when we press it, it stays on, and we can read that on state as a 1. When we press it again, it goes off. We can read that as a 0, but calling it a 1 or a 0 is how we interpret it. It's actually just on or off, lighting a switch, a light or not. But we interpret it as a 1 or 0, and it becomes a binary representation for the state of the switches at any point in time. So although we use this as a counter, it is also memory, and we can count it as memory and holding information. And that's the key to digital electronics. Now, I thought doing a couple of circuits in relays to illustrate that might be of interest, it might be helpful, people might want to play with it, but if I'm going to do something real with it, of course I'm going to go and buy a board, but at least I understand what's going on in that board. Anyway, I hope you found the video interesting. Thank you very much for watching, and please do remember to like and subscribe.